Last time, we derived the London equation in the superconducting state, and the supercurrent obeys this relation called the London equation, which is minus constant prefactor times the vector potential A, and this linear relationship between the supercurrent and vector potential will lead to so-called Meissner effect, which we will derive in just a moment. To derive the Meissner effect, we need to take advantage of the Maxwell equation that we are all familiar with. So one of the Maxwell equations says that this curve of B is 4 pi over C times charge current J. And here J in the superconducting state is the supercurrent vector, Js. And we also know that the B field, the magnetic field, is related to the vector potential by this curve of A. So then we could combine all these relations and we could calculate this double curve of B, which is the curve of B. And you want to calculate this quantity, then you could take advantage of this Maxwell equation. So this curve of B is what? This 4 pi over C times this J vector, and therefore this is the curve of J. But what is J? Well, J is Js here, and Js is given by the London equation. So you plug in the London equation here, you get some complicated prefactor times the curve of A. What is curve of A? From your Maxwell equation, know that this is B, right? So you immediately recognize that on the right-hand side of the equation, it is some constant prefactor times the magnetic field, B vector. But on the left-hand side, this curve of B, based on your applied math or mathematical physics, you know that this is given by this gradient divergence of B minus Laplacian of B, or gradient square of B, right? But we know that since there is no magnetic monopole in this system, so this divergence of B vanishes, right? Because from the Gauss law, divergence E is given by the charge that you enclose on the surface, but there's no such magnetic monopole, and therefore divergence B vanishes. And the left-hand side of the equation is given by just the minus gradient square B. So you could just combine these two sides of the results. You get this gradient square of a B is given by B vector times this prefactor, constant. And this constant prefactor, 4 pi, so-called superfluid density NS, effective charge E star square, and effective mass M star and C square, and altogether is defined as 1 over lambda L square, where lambda L is given by the square root of this quantity, and this lambda L is so-called the London penetration depth or London penetration length, which we will discuss just a moment. But this equation could be solved very easily from your second year maths. You know that this solution is nothing but exponential function. And in particular, this physical solution corresponds to the exponential decay. And that's how this Meissner effect comes about. Because the magnetic field inside the superconductors, like this on the right-hand side of this figure, corresponds to the superconductor. On the left-hand side of this x-axis is actually the vacuum. So the boundary is the y-axis. Suppose I apply the magnetic field B0 pointing to the y direction, okay, with the magnitude B0, then this size of the magnetic field along the y direction is going to decay. Okay, so if you make a plot of this B0, the size of the B0, the magnitude of B0 really decrease quickly, and how this B0 decays, when this B field penetrates inside the superconductors, satisfy this exponential decay, right? And the half width of that decay length is precisely this lambda L, London penetration depth. And this is the accurate description of the Meissner effect in the sense that this magnetic field does penetrate into the system. However, the London penetration depth is really short, so that the magnetic field, this magnitude of magnetic field decays really fast, and it decays exponentially, And for this whole system, on the right-hand side of x-axis is the bulk material. And, compared to the size of the system, lambda L, London penetration depth, is really, really negligible, which means that, roughly speaking, the magnetic field does not penetrate into the bulk because the London penetration depth is usually really, really small in magnitude. But it does penetrate. But the penetration depth is really, really tiny. So let me give you some estimation of this lambda L for some high TC superconductors. This is T, and this is TC, and this is lambda L, and this lambda L goes like this. So lambda L is given by this quantity. Let me just repeat that one more time. But this time, I intentionally, separate these two factors. Okay, this NS corresponds to the, supercurrent density, charge density, so-called superfluid density. So in the superconducting state, NS is finite, but in the normal state, when T is actually larger than Tc, then this quantity is 0. Okay, so NS is 0 when temperature is greater than or equal to Tc. So, but you can see very clearly that when Ns goes to 0, then this Ns factor, square root of Ns, appears in the denominator of the lambda L. As a result, when Ns goes to 0, lambda L goes to infinity. And this is exactly what happened here, that the London penetration depth goes to infinity as T goes to Tc. And this is the experimental data that I plotted here. The blue curve indicates that the London penetration depth increases with increasing temperature for T below Tc, but right at T equals Tc, lambda L diverges. And of course, for T above Tc, there's no Ns. As a result, lambda L is ill-defined. Okay, so that there's no superconductor anymore, and it doesn't make sense to define the London penetration depth. The magnetic field can freely penetrate into this as a normal metal. But in the superconducting state, lambda L follows this blue curve. And in the 0 temperature limit, you could extrapolate this lambda L 0 to the finite value, but at finite temperature, it goes like this way. And the magnitude of this lambda L for different systems are actually listed here for, say, YBCO, the cuprate superconductors. The London penetration depth along the C-axis is usually different from the London penetration depth in the AB plane. So lambda AB is like a few thousand Armstrong, but lambda C, when the magnetic field points to the C-axis, is about, say, 1/3 of that lambda AB. So still very, very short distance, because 1,000 Armstrongs 10 to the minus 10 times 1,500 meter, right? So it's really, really short. And your sample is how large is this? Maybe sizable. You could see that superconducting thin film, it's the order of, say, centimeter or so. But then this is way too small. So that's about the Meissner effect. Okay? So of course you could find all this lambda L for different normal metals. But this is niobium, this is tin. It's about a few hundred Armstrong. And you could look at all the tables in your textbooks regarding this London penetration depth for different metals. So in a few hundred to a few thousand Armstrong. So based on this phenomenology, we know that once the electrons are in the superconducting state, they have such a Meissner effect. And supercurrent satisfies the London equation, and we get Meissner effect. So this is the most important properties of a superconductivity. But of course, this behavior is tied to the fact that this resistivity vanishes for temperature below Tc, right? So this is resistivity, and this is Tc, but we don't have time to really derive from the pure quantum mechanical theory, namely the BCS theory. to show that indeed there is no resistivity, okay, once the electrons are in the superconducting state, which shows Meissner effect. But this is a consequence of this Cooper pairing and Meissner effect. Good. So let's take a short break. When we come back, we will use this observation and phenomenology to argue that due to electron-photon coupling, two electrons can actually stick together due to this attraction, and they form Cooper pair. And what is the nature of this Cooper pair regarding the spins of these two electrons? And we will talk about that in just a moment. By the way, you could look at all these equation formulas and figures in any references, especially Ashkerf-Mermion and Kittel's first book, which give you a very detailed description of this phenomenology and those properties and those this London penetration depths and so on. But the underlying physics of the superconductivity in ordinary metals, as I mentioned, will be described by the BCS theory, which is absent in any introduction level of solid-state physics. And this is a big miss or big loss for graduate students who learn solid-state. And this is precisely the reason why this course can offer you a complete understanding of this phenomena. So let's talk about the Cooper pairing. Okay, so as I mentioned, two electrons may feel attraction between them because of the electron-photon coupling. What is the physical picture of this Cooper pair look like, especially, the spins of these two electrons, and why are they anti-parallel to each other, and how can we describe such a Cooper pair? So this is a very important issue before the BCS theories is introduced. So to see this Cooper pair, we need to go back to this classical mechanics and classical electrodynamics. So in both classical mechanics and classical electrodynamics, we know there's a difference between so-called canonical momentum and this m times v, which is the naive definition of the momentum. So the canonical momentum, which we call this p, is not simply just your mass times velocity, which is the case in the ordinary classical mechanics. But in the presence of the charged particle, in the presence of the field, it is given by this definition, where there's additional term due to the electromagnetic field or vector potential, and which contributes to minus E star over C times this vector potential A. And so in electrodynamics, the momentum of a charged particle in a canonical way should be defined in this fashion because of this so-called gauge field, okay, external gauge field, or the vector potential term which couple to the charge. And as a result, when the charged particle move, the momentum that leads to the standard kinetic energy of the Hamiltonian of the charged particle should be defined this way. Okay, in addition to the m times v, we need to add this extra vector potential term. So if you are not familiar with this canonical momentum, and you should go back to the classical EMN and check the definition of the canonical momentum. So here, in the superconducting state, the supercurrent, as I defined, is given by minus this superfree density and S times effective electric charge times the velocity of the charged particles. But what is the velocity of the charged particle? You could just rewrite this in terms of the canonical momentum, P, which is this. So if I plug in the definition of the canonical momentum of a charged particle in the superconducting state, and I could rewrite the supercurrent, Js, in terms of a canonical momentum, P. So this is a momentum of a Cooper pair, or if you like. Or in the superconducting state, the momentum of a charged particles that lead to the supercurrent. But what is the second term? So immediately recognize that the second term is nothing but the supercurrent because of the London equation. So if I look at the second term, which is linear proportional vector potential A, and you could multiply all this prefactor, including the minus sign, and this is precisely this London equation is telling us. This is simply just London equation, but if I compare this equation, between the left-hand side and the right-hand side of the equation, I get Js on the left-hand side is given by minus ns E star over m star times canonical momentum P plus Js. This sounds very weird because on the left-hand side you got a Js, which is here. But on the right-hand side you got the Js as well, and minus a term which is linearly proportional to the canonical momentum. And you immediately cancel this. So Js cancels with that Js on both sides of the equation, and you lead to the very strange but very important conclusion that the canonical momentum in the superconducting state of a charged particle vanishes. Okay, so this is a very, very important conclusion which helps the BCS to propose their theory for superconductivity. And let me just emphasize the importance of this result. So this tells us that the net canonical momentum in the superconducting state is 0. So how come the momentum of electrons in the superconducting state could be 0? We just said that there's a supercurrent, there's a charge flow without dissipation, so there should be a finite or very large momentum for the charged particles in the superconducting state. How come this momentum vanishes? But to understand this, we need to understand the following. So if electron can pair up with another electron across the Fermi surface, it is possible to satisfy this condition. So let me just use a cartoon picture to illustrate this. So this is the Fermi surface, and we know very well that this electron-photon coupling gives you some modification of the Fermi surface and also the photon frequency, but we'll see later that this between the range of this Debye energy, so electron-photon coupling applies. But we know that at low temperatures, all these active electrons are close to the Fermi surface, and suppose I have an electron here carrying plus Kf, and I have an electron there carrying minus Kf. Now if these two electrons are paired up, then if I sum over all this momentum of these two electrons, I got 0. So this is electron number 1, this is electron number 2. So which immediately indicates that this attraction between these two electrons must come from the opposite side of the Fermi surface. One electron carries Kf, another minus Kf, so we sum up these two momentum of these two electrons, got 0. Bingo. Okay, so I believe this is the reason how this BCS got an idea that two electrons across the Fermi surface can form Cooper pair. So this is really key point of the BCS theory on a qualitative level, that because of the London equation, and we immediately, and also the attraction between two electrons due to electron phonon, and we immediately get a conclusion that two electrons come from the opposite side of the Fermi surface must form a pair, which will satisfy this 0 canonical momentum. But what about the spin? As I mentioned in the cartoon picture, that two electrons across the Fermi surface may form a Cooper pair like this, and the spins are indicated by the arrows. One is pointing up, another pointing down. How does this picture come about? And to see this antiparallel spin orientation of two electrons inside a Cooper pair, we should go back to the Pauli principle, of course. The antiparallel spin in the Cooper pair electron comes about because of a Pauli exclusion principle. As I mentioned, we know very well from the quantum mechanics that for two electrons, and they can form two electron wave function or two-body system. Okay, so we know very well that by Pauli exclusion principle, two electrons of the same state cannot occupy it in the same position, or two electrons cannot go to the same state. Right? Okay. So that is the situation here. So this is a special dependence of this wave function of the two electrons in the two different situations. One is the situation where these two spins are parallel to each other. Okay, and another is a situation when these two spins are antiparallel to each other. Okay, so we know immediately that by Pauli exclusion principle, when the two electrons carry the same spin, they never come close enough, or they never overlap in the same position. So this is, say, R, because of the Pauli exclusion principle. So there's no probability, to find this, two electron systems when they overlap, if they carry the same spin. So the spatial distribution of this two electron wave function for parallel spin configurations must be like this, because anti-symmetric nature of this fermion wave functions. So they must satisfy this anti-symmetric properties when you exchange this two fermion. However, if these two electrons occupy the opposite spin configuration and they can't come closer with a finite overlap of these two wave functions, and therefore there's a finite probability at 0 when these two electron wave function can overlap. And we know that since these two electrons can pair up in the same state, so-called the superconducting state, these two spins cannot be the same, because this is something like the same quantum state, which we will talk about later as a many-body wave functions. But just look at these two electron wave functions like this. Okay, if we consider these two electron wave functions a single quantum state, then the individual electrons must carry opposite spin. Okay, just like this Pauli exclusion principle said that when these two electrons come closer and they overlap, their spins must be antiparallel to each other. Okay, but of course this quantum state or the Cooper pair state is in the momentum space, but this is the real space. But this Pauli exclusion principle applies in both real and momentum space representation of the wave function. Okay, so because of the Pauli exclusion principle, these two electrons staying in the same superconducting Cooper pair state must carry the opposite spins. And as a result, this is a correct picture of a Cooper pair, and this is the starting point of the BCS theory. That we start from this cartoon picture, that we imagine that at a low enough temperature and electrons can actually form such a Cooper pair, and we could simplify this BCS Hamiltonian based on this cartoon picture. So I think this tells us a very important lesson. The lesson is that all these new discoveries, both in theory and experiments, come from the observations. Observations are based on these experiments, or some simple relations, or simple fundamental physics principles, and we cannot violate. Okay, so you can see that based on the London equation and Maxwell equation and Pauli principle and electron-phonon coupling, which is attractive, and you just combine all this, facts, and this idea of the Cooper pair simply emerges. And as a result, this kind of a new concept of new kind of particles or a new quantum mechanical effect is not coming out of nowhere. It is simply the direct consequence of all these new observations or experimental results and physics principles, that when we combine all these existing results, and this is a natural consequence of these observations. Okay? And so I guess this is a very good example telling you that whether you are a theorist or experimentalist doesn't matter. So if you think about the new physics, this must come from new experiments and basic fundamental physics principles. And just by thinking these facts thoroughly and carefully, and then you will discover new things. Either experimental new discovery or theoretical new discovery. And this is a very good example of that. Okay, so let's take a short break. When we come back, we will construct the BCS Hamiltonian based on this idea. So for this part, you could look at Flansburg. I don't know what chapter is that for the BCS theory at the very end of this book. So once we know this, the underlying reasons behind the Cooper pairing, like what I just mentioned, and it is not strange at all, it is really natural that you have a Cooper pair. Okay, so it's not counterintuitive. On the contrary, you should appreciate this quantum mechanics that give us such a wonderful understanding and complete understanding of ordinary superconductivity. So let's continue. So the BCS proposed such a Hamiltonian to describe the superconducting state in ordinary metals, and this Hamiltonian looks very similar. In fact, it shows the same structure, mathematical structure, as Coulomb interacting electron gas. And remember that when we talk about the Hartree-Fock, and this is the Hamiltonian of that Hartree-Fock system, where, say, two electrons are scattered by Coulomb interactions, and this is the potential term in Hartree-Fock. And remember, this 2 pi e squared over q squared is the repulsive Coulomb interactions between two electrons. And we sum over k prime, and the spin s and s prime, and also this momentum transfer q. So here, in this electron phonon system, which mediates the attractive electron-electron interactions, we have almost exactly the same mathematical structures as that we discussed in Hartree-Fock, except now this matrix element, or the potential term W, is the electron phonon mediated attractive electron-electron interactions. Remember, when these two electrons energies in the denominator almost cancel out, and you immediately get attraction because this is minus sign, right? Okay, so the difference between this Coulomb interacting electron gas and electron phonon mediated attraction between two electrons is simply due to the different forms of the potential term. And we should replace this Coulomb potential by this electron phonon mediated electron-electron attraction like this. Other than that, they are identical. Okay? So we could take advantage of such a Hamiltonian, and we could simplify this based on this Cooper pairing that we just described. And remember, when you sum over all this momentum k prime and spin, s prime, and momentum transfer, we need to impose the Cooper pairing. Okay? So this is the cartoon picture of the Cooper pairing, telling you that two electrons come from across the Fermi surface, carrying momentum k and minus k, and also, say, spin up and spin down, and they get scattered by electron phonon interactions, and then they get scattered out, and the momentum transfer is q, which leads to the upspin electron carrying k minus q as a scattered momentum, and the spin down electron carrying minus k plus q. So this is the scattering diagram in the BCS theory, which looks pretty similar to the electron-electron Coulomb interaction, except we know that these two electrons across the Fermi surface must come in pair, and they should interact with the other two electrons by electron phonon. Okay, so the red circle represents this Cooper pair electrons on the left-hand side in the initial state, and the final state still a Cooper pair, but the momentum got shifted a little bit by q. But this q is really, really tiny. So we will see later that this is so-called small momentum transfer limit. Then you recover all this the superconducting gap NTC that has been observed experimentally. Okay, so in other words, in the low temperature limit and the small momentum transfer limit, and this picture helps us to understand, the low temperature properties in the superconducting state of the normal metals. So let us just apply this Cooper pair proposal, and to simplify this so-called Coulomb term, or this potential term, and by summing over the spin indices. So we know that if this electron number 1 carry momentum k and spin up, and another electron must be minus k carrying spin down state. So therefore, although we sum over both spin indices SS and prime, so it looks like there are 4 possibilities, but in fact there are only 2 possible states, right? So whether this k up pair up with minus k down, or k down with minus k up. That's it. Okay, and therefore we could simply just write down these 2 possibilities. First, that this k, with a minus spin, and another turns k with a plus spin. So once this spin attached to this k is fixed, then all the other spins are fixed. Okay, but you could rearrange all this operators of these 4 fermions, and you can show that since this k and k prime are dummy summing variables, so it doesn't matter which name I call this. I can call this k prime, or I can call this k prime k. I can call this k any name I like. So when I sum over both k and k prime, it doesn't matter. Okay, and as a result, these 2 terms gives you exactly the same contributions. So if you interchange the labeling or these variables between k and k prime, you'll see that this term is identical to that term. So as a result, we simply just put the factor of 2 and doesn't care about the difference between these 2. So now we know that this momentum of the Cooper pair electron is actually tied to the spin. As a result, we don't bother writing down the spin, because we know that when I write this momentum k, it implies that this electron carry momentum k and spin up. But if I write this operator as a minus k here, it tells us that this is electron carrying minus k and spin down. So then I don't bother expressing all the spin indices. And this is my convention, and this convention is correct. So let's just combine, as I mentioned previously, that these 2 electron-electron interactions, namely the Coulomb interactions, which is repulsive, and also electron-phonon-mediated attraction, both interactions are present in metals. So we need to sum over these 2 interactions. But then we know from this Cooper pair idea that these 2 electrons must pair up like this. So we know that the ground state should follow this kind of pairing, and as a result, we could just change the variables in the Coulomb term the same way that we did for this electron-phonon term. But then we need to sum over these 2 contributions as a potential term. And as a result, I could simply just use the same mathematical form to combine this Coulomb term and electron-phonon-mediated attraction. And remember, this minus sign here indicates that the interaction is negative or attractive. And therefore, the magnitude of the VKK prime must be positive to guarantee that this is the attraction, because there's an overall minus sign here. And the factor of 1/2 here is to avoid double counting when you sum over both KK prime and spin indices. Okay, so inside this matrix element VKK prime is a sum over these 2 interactions. So remember, the Coulomb interactions, the Coulomb potential is actually repulsive, and as a result, this is plus, because it's a minus sign and minus sign, right? So it's a plus sign, and this UKK prime is a Coulomb term, which is plus. But this electron-phonon-mediated electron interaction is actually minus, because this is attraction, right? And minus actually cancelled, and then this is attraction, so this is minus. Therefore, if this net potential VKK prime is positive, this tells us that the size of the attraction must be greater than the size of the repulsion. or the magnitude of the attraction should be larger than the magnitude of the repulsion. Okay? And this is indeed the case, as I mentioned, when both K and K prime are very close to the Fermi surface and they follow the Cooper pairing mechanism, and for sure, electron phonon mediated matrix element W, the size of that W matrix element should be larger than the size of the Coulomb term. All right? So this is a fact. Okay? So this tells us that the net. So of course, and this argument is based on the phenomenology of superconductivity on the metals. If the net interaction between two electrons is repulsive, then we don't have the superconductivity. Okay? Because the two electrons feel repulsion, and there's no way that they compare. Okay? So because we know that this phenomena, the superconductivity phenomena, exists in nature, and therefore this attraction must be, the size of the attraction must be larger than the size of the repulsion. But you could also measure the size of the attraction mediated by the electron phonon and the Coulomb energy. Okay, so I haven't tried that, but you could look at literature and see the comparison between this, the magnitude of these two interactions. But anyway, so let us just assume that this is just some positive value which guarantee that this interaction is attractive. Okay, so now we can formally write down this BCS Hamiltonian, which we will analyze just a minute. And as I mentioned, I forget about the spin indices. It doesn't mean that the spin indices are absent. It's just because the Cooper pairing, this momentum K must links to the spin up and minus K with spin down. So, whenever I sum over positive K, the spin is up, and negative K, the spin is down. That's it. Okay, so I forget about the spin indices. And this is, if I separate this positive and negative momentum, and I just look at this sum over momentum K, which is positive, then I should repeat the negative energy part, right? One more time. And then this is the attraction. Remember, there is a factor of 2 when I sum over spin, and I can, forget about the spin indices because I know these two terms are identical, so there's a factor of 2, and this factor of 2 cancel this 1/2 factor, so that this prefactor is 1. So, good, this is the starting point of the BCS Hamiltonian. So, next we will do something about this BCS Hamiltonian, and we could simplify this calculation with the help of some so-called mean field approximation. Good. So let's take a short break, and when we come back, we will analyze this BCS Hamiltonian and what is the eigenenergies and so on and so forth. So this Hamiltonian looks very similar to this Hartree-Fock. However, we should remember that two electrons should come into pair, so they should be created at the same time, and they should be destroyed at the same time. Okay, so unlike the plasma oscillation physics, where you have electron-hole pair excitations, so in the BCS theory, we have two electrons coming into pair. Okay, as a result, we should simultaneously create two electrons in a Cooper pair, and then we should simultaneously destroy them. And so all these excitations are no longer electron-hole pair-like. Okay? Instead, it is a different type of excitations called the Bogoliubov excitations. Okay? So based on the BCS idea, we should use this Cooper pairing to diagonalize this so-called mean field BCS state and find the eigenvalues. So we could take advantage of so-called Nambu basis, which is the 2x2 matrix representation of the BCS Hamiltonian, which we'll describe in just a moment. And also the BCS assumption. So let me just rewrite this Hamiltonian, but including the spin indices. And we impose this BCS assumption here. So the BCS assumption is this. They assume that the matrix element VKK prime is roughly a constant near the Fermi surface, over a window of the plus minus dBi energy. So as I mentioned, electron-phonon coupling ranges plus minus dBi energy relative to the Fermi energy, right? So this is the inner shell and this is the outer shell, right? So all this electron stays within the range of the plus minus h bar omega d relative to the Fermi level could interact via electron-phonon coupling. Okay, so the simplest assumption, of course, is a very bold assumption, whether this matrix element is a constant, inside this plus minus h bar omega d range relative to the Fermi level, whether this V effective is really a constant. But anyway, it turns out that this assumption is really good and really naive and simple, that the this potential matrix element VKK prime is independent of momentum, okay, within that range plus minus h bar omega d, which is just a constant. Of course, this is assumption and approximation, and we will come back to this approximation later, whether this approximation makes sense. Of course, the answer is yes, this approximation works really well, otherwise we don't get the BCS theory, like the theory that we know today. And as a result, this V effective is approximately independent of momentum k and k prime, and I can pull out this factor VKK prime square, which I call this V effective square, because it is proportional to the square of this electron-phonon matrix element. Okay, so in other words, this electron-phonon matrix element is a constant within that window. So this is the BCS assumption, and then, of course, from the Cooper pair idea, these two electrons must form pair. In other words, if I take the ground state expression value, I could expect that this expression value is finite, indicating that these two electrons can be created or destroyed simultaneously, and this quantity is non-zero, which means that these electrons across the Fermi surface carrying k up and minus k down form a pair, and they are related to each other. So if I measure this excitation value in the BCS state or the superconducting state, and I get finite value, I get non-zero. So if they are not related by this Cooper pairing, then this, of course, vanishes. Because in the ordinary metallic state, this expression value, of course, is zero. So you cannot simultaneously create or destroy two electrons with opposite spin and across the Fermi surface, because there's no such attraction between these two electrons, right? So if there's no, say, electron-phonon coupling, just ordinary metals, this so-called expression value must vanish. And just because of this Cooper pair in the superconducting state, and this quantity is finite. And this quantity is playing a leading role in this BCS Hamiltonian, because we know that at low enough temperature, this pairing should dominate the ground state property. We expect that this thing will dominate. As a result, we can make a further approximation called the mean field approximation. And this average, or this acceleration value of the C dagger k up, C dagger minus k down, is called the mean field. Just like what you have learned in this magnetic property of solids, like we have a Weiss mean field, which we will discuss in the magnetic chapter. But you can consider this just some number called the mean field number. It's kind of an average, quantity that this two electron can pair up in that Cooper pair state. And this is just a number, and it is not the operator anymore, because we already take the average. And when we take this ensemble average or thermal average or this, say, ground state average, and this quantity is just a number, right, in quantum mechanics. But we imagine that this quantity should play the leading role in the BCS ground state. And therefore, we could further simplify this 4 fermion operator. We know that these two operators must be related, and these two must be related, okay, in that way. Okay? As a result, we could make the following mean field approximation, that this 4 fermion term is approximately given by this mean field variables. So the mean field could be taken for Dagger pairs or non-Dagger pairs, and of course you should sum over these two possible pairing. So this quartic or 4 fermion term could be approximately given by this mean field number multiplied by the remaining operators, 2 operators. Okay, so namely, I could consider this as some kind of approximation that I simply consider the effect of the quartic coupling term as an effective sum mean field times the remaining 2 operators and plus the other way around. Okay, of course, this is approximation, but the assumption behind this approximation is based on the Cooper pairing. Namely, these 2 electrons must develop some non-zero expression value at ground state, and these 2 will do the same thing. Okay, but we can, of course, this Hamiltonian cannot be just a number, so it must be some quantum nature which comes about when we simply just keep the remaining operators there, and just by approximating this the other 2 operators as their mean field. Okay, it's like some classical value number multiplied by these 2 operators, and therefore we simplify this 4 fermion operator term, and we transform this quartic term into the quadratic term, where we have only 2 remaining quantum operators, and the other 2 form pairs, and they are approximated by their mean fields. Okay, of course, there's some errors or some something which are missing here, and that's why this is approximation. But this approximation turns out to be very good, and it gives us almost the same value that was observed experimentally. This approximation is called the BCS mean field approximation. It's really a remarkable achievement, because such a simple and naive assumption that this interaction matrix, electron phonon matrix elements is a constant across the Fermi level, and also we could just make a further approximation by assuming that this operator is nothing but a mean field, and as a result, this quartic operator becomes a quadratic. But this quadratic is very different from all the existing known examples, and this is called the BCS mean field Hamiltonian. So let me just repeat what I just have done. All right, so the potential term consists of the constant potential strength, and inside the summation of K and K prime, we have the mean field approximation. That this 4 fermion term is reduced into the 2 fermion operator multiplied by the mean field, but of course this mean field value should be determined self-consistently, and we could define such a mean field variable multiplied by this V effective square, and we should see later that this is nothing but the BCS gap, the energy gap which protects the BCS state called the gap function. The BCS gap function is nothing but this magnitude square of this electron phonon coupling times summation over all this mean field variables of Cooper pair electrons. And later we will derive the equation for this BCS gap, and we could self-consistently solve for this BCS gap as a function of temperature, and also we know this transition temperature Tc. But we could further simplify this BCS Hamiltonian by expressing this in terms of delta or BCS gap. And this gap function could be in general complex, could be a complex number in general, because we don't know at this point whether this expression value gives you a real or an imaginary or complex number. It can be anything. So then we could actually assume that this is a complex number, and we can simplify this BCS Hamiltonian in terms of this BCS gap function delta, and we will derive the equation for delta and for Tc, and also the eigenvalue and so on and so forth. And this is a new type of Hamiltonian that we haven't studied before. The reason is that all this Hamiltonian that we studied so far are quadratic in operators, and the quadratic is always in the form of the C dagger C or B dagger and B, right? And this is the first time that we have such a quadratic operator, which is this destruction of the two operators and creation of two operators. Namely, the CC and C dagger term are the new terms that we haven't studied yet. Okay? But of course, we are able to find the eigenvalues if we have such a BCS type of Hamiltonian, and it's just the way that we find the eigenvalue is to diagonalize this so-called Nambu-based 2x2 matrix. So by the way, Nambu is a Japanese theorist who got a Nobel Prize in early 2000s, and because of some contributions in high energy physics, but he also contributed to the condensed matter by proposing such a very convenient matrix representation called the Nambu basis. And Nambu basis is this kind of a 2x2 matrix construction of a BCS Hamiltonian. Suppose that I can form a row matrix, say 1x2 or 2x1 row matrix consisting of this two operators C dagger K up and C minus K down, and I could fill up this 2x2 matrix element, and I can show that this is exactly the same as the BCS Hamiltonian right there. And by the way, this is the homework. Prove that H Nambu is the same as HBCS. Okay, so as I mentioned, you are familiar with these rules of matrix products, right? Matrix multiplications. So this is the matrix product among three matrices. One is, say, 1x2 matrix, and the second one in the middle is actually 2x2 matrix. And the third on the right is actually 2x1 matrix. As a result, from your high school mathematics, you know that a matrix product among the 1x2 times 2x2 times 2x1 is actually a 1x1. Okay, so it is very easy to see that if you simply just expand of this matrix elements of this matrix products, you go back to this BCS Hamiltonian. Okay, it's very easy to prove. Okay, so we take a short break, and then we continue diagonalizing this 2x2 Nambu based BCS Hamiltonian. So you can see that the Hamiltonian of the BCS theory is simply just to find the eigenvalues, the eigenstates of this 2 by 2 Hamiltonian matrix, which you can do very easily from your quantum mechanics knowledge. And from your quantum mechanics, you know that if I represent some quantum mechanical Hamiltonian in terms of, say, the spin 1/2 system in terms of a 2 by 2 matrix, and the eigenvalues corresponds to the eigenenergy of your system, and the eigenvectors are the eigenstates for the corresponding eigenvalue. Therefore, the remaining job is to find the eigenvalues and eigenvectors of this 2 by 2 matrix, which you can do within 1 minute. And simply just finding the eigenvalue of this 2 by 2 matrix is to find the solutions of the determinant of the 2 by 2 matrix, right? Okay, so let's do it. So it is very easy to see, but we need to discuss so-called Bogoliubov quasi-particle operators. So this diagonalization of a Nambu Hamiltonian of the BCS theory is called a Bogoliubov transformation or Bogoliubov diagonalization, and the new quasi-particle that is formed by linear combinations of C and C dagger are called Bogoliubov quasi-particle operators. And how to define this or find this Bogoliubov quasi-particle operator equivalent to actually diagonalize this 2 by 2 matrix. Okay? Remember, in your applied maths, you know very well that when you try to diagonalize the matrix, you should find this unitary matrix, right? And by unitary transformations, and you could show that under such unitary transformations, this Hamiltonian is diagonal or diagonalized. And this unitary matrix is called U dagger here, or U is made of the coefficients that corresponds to this eigenvector, so which I will mention just a moment. Suppose that there exists such a unitary matrix U, which is a 2 by 2 matrix, and you can show that U dagger H Nambu times U is actually diagonalized. So this is as simple as that. Okay, suppose I have these coefficients U, K, V, K, and so on and so forth, and if I define this U this way, and I will find this U and V later, but suppose this exists, and the way that I diagonalize it is follow the standard unitary transformations of the matrix, and at the end of the day, I get these two eigenvalues appearing along the diagonal direction of the 2 by 2 matrix and 0 along the other off-diagonal direction. Okay, and this transformations that takes you to the diagonalized Hamiltonian is called the Bogoliubov diagonalization or the Bogoliubov transformation, and which tells you that by forming the linear combinations of a C and C dagger in the Cooper pair state, we could use the new operators called the Bogoliubov quasi-particle operators, and gamma, and the gamma K up or gamma dagger K down are the Bogoliubov quasi-particle operators. In that basis, we could diagonalize the 2 by 2 matrix. And it is very easy to see this eigenvalue, EK1, is nothing but the plus of this square root, and EK2 refers to the minus of the square root of this epsilon k minus mu squared plus delta square. Okay, so let me just summarize this 2 by 2, and the eigenvalues and eigenvectors are such that you have a UK minus VK, VK, and VK star, and UK star corresponds to minus EK. And UK is defined as 1/2 minus chi of k, and VK square root of 1/2 plus chi of k, and chi of k is this epsilon k square plus delta square root, and effective 1/2 here. Okay, so I leave this to you as a homework exercise. This is a simple exercise. this. Okay, it's the same homework, and which consists of one part and part 2 and part 3. Part 1 plus part 2 plus part 3. Great, I think that's enough for today, and then we will finish this BCS theory. The remaining time of the semester, we will come back to the magnetic properties of solids and try to review and preview all the chapters and sections that we have discussed or we will discuss.